Hello! In this video we're going to be finding a diagonalization representation for matrix A. So this is where all the theory that we've learned comes together and all the examples really come together. It's quite exciting. Really enjoyed learning this when I was taking linear algebra. We're going to use an example that we have for quite some time now. We're going to be using the example of that linear transformation which reflects vectors in R2 in the plane and takes them to vectors in the plane when it reflects it about the line y is equal to minus x. And you may recall we found that transformation before. We use that change of basis. So we have t of x is equal to ax, where A is this matrix here. 0, -1, -1, 0. Okay. So we're going to be using the idea of these eigenvalues and eigenvectors. Now that we know how to find those, we actually have a really nice theorem that helps us find that diagonalization, that diagonal representation. So to create this diagonal matrix D, an invertible matrix P such that we have D is equal to P inverse AP, that is the definition of diagonalization. We're going to be using the eigenvalues first. So you may recall the eigenvalues of A for this matrix were 1 and -1. We talked about why that was, because for a reflection we took a vector in the direction of that line and it just stayed there. That corresponds to eigenvalue 1. And then we took another vector that was perpendicular to it, and we saw that that reflected the vector about that line in exactly the opposite direction, so that was where we got that -1 eigenvalue. But we also talked about how to find these using the definition and grinding it all out. We also have the associated eigenvectors of this matrix were -1 and 1 for 1. That was one of the vectors that we found. Remember, that was in the direction of the line. And then 1, 1 was perpendicular to the line. That one corresponds to -1. So here's our representation. By our theory, our diagonal matrix is just going to be a diagonal matrix with zeros on the off diagonal, and on the diagonal we'll have those eigenvalues. I chose to put 1 up here at the top and -1 at the bottom. I called those lambda 1 and lambda 2. And the corresponding eigenvectors will make up this matrix P. So the eigenvectors corresponding to 1, if I put 1 first, I need this vector 1 first in this representation. I have to have it that way. So I have -1, 1 for this column, and 1, 1 corresponding to that -1 eigenvalue for the last column. So now I have this representation and I didn't really have to do any work. Well, of course I had to find the eigenvalues and vectors, but that did my work for me. So if you have a linear transformation like this, we can use this idea, which is really cool. So our representation would be this diagonal matrix is equal to P inverse AP, where again the A is the matrix that was given, the P is the matrix given by the eigenvectors, and if we multiply these three things out, we would get that diagonal matrix with the eigenvalues on the diagonal. How does this all really tie in with things that we've learned? Well, we know now that a better basis to work at for this transformation than the standard basis would be this vector in the direction of the line and the one that's perpendicular to it, and those are specifically the eigenvectors of A. So if you find the eigenvectors of A, then you have a great basis to work with. It will work even better than the standard basis, which we're all used to working with. But that's the idea of why we need to change bases sometimes. And I'm going to show you this diagram one more time here. What we know now is we had these change of bases and we sort of maybe wondered why we were doing that at the time, but now we sort of have a nice way to look at this. So the standard matrix A would take a vector in R2 and apply the transformation to that vector by multiplying A times that vector and take it across to R2. However, we could find an alternate representation for that. Finding this matrix P, given by the eigenvectors here, if we multiply that P by V, we will get this B coordinate vector with respect to that new basis, the one that we like to use. And we have this new matrix D, which they called A prime earlier. This is the matrix of T with respect to that other basis, the basis of these eigenvectors here. And those are with the eigenvalues in the diagonal. So if I multiply D, I go from this to this. Now this is going to be the transformation applied to those vectors with respect to B. And then, of course, I can take it back here using P inverse. So this brings our theory, as you could say, full circle around, and it might give you a reason why we'd want to use something other than the standard basis. And these eigenvalues and eigenvectors can totally help you with that, so you don't have to make it too hard. I hope this has helped. Thank you very much.